In the beginning, there were 5 notes, 0, 4, 0, 9, 7, 16 notes in the scale of G minor. Subtract 1 octave. The sound was a sawtooth wave, tamed with acid. Visualize the lead. Next, kick drum, trance kick drum, 4 on the floor, with the scope. Increase the power by ducking our lead with the kick. Targets 3, 4, 5, 6. Next, bass. The sound should be a superstar. We need more chaos with random detuning of the superstar.
All right. It is 1:50. I'm just say 2. It's probably take me a couple minutes to get started here. So I have a thing at 4 p.m. that I need to stop for. It'll probably just take a couple minutes, but I will stop there. So I got about 2 hours roughly. I'm actually going to set a timer so that I do not forget. Because I get in the zone sometimes, and let's see, 4 p.m. Alright, so I got my timer up there. So I'll hop off at 4 and I'll come back on probably 4:15, 4:20, something like that. 4:30 at the latest. Alright, so let's get through job control. I'm actually going to stand back up, because I kind of like reading and standing. Standing while I read. And kind of move around a little bit more. Alright, job control. I think that's where we left off. Job control is a feature that first appeared around 1980 in the C shell on BSD. Job control permits a shell user to simultaneously execute multiple commands jobs, one in the foreground, others in the background. Isn't that what we've already been discussing with the process groups and sessions and stuff? Jobs can be stopped and resumed and moved between the foreground and background, as described in the following paragraphs. The initial POSIX 1 standard support for job control was optional. Later Unix standard made it mandatory. In the days of character-based dumb terminals, physical terminal devices that were limited to display ASCII characters, many shell users knew how to use shell job control commands. With the advent of bitmap monitors running the X Windows system, or Wayland now, Wayland Hyperland like I'm running, knowledge of shell job control is less common. However, job control remains a useful feature. Using job control to manage multiple simultaneous commands can be faster and simpler than switching back and forth between multiple windows. For those readers unfamiliar with job control, we begin with a short tutorial on its use. We then go on to look at a few details of implementation of job control and consider the implications of job control for application design. I guess this is going to talk about like foreground, background, jobs, like all those commands. So if we do a grep for sighup and user source Linux, pipe it to X, throw it in the background. We can sleep for 60 in the background. Gives us the job ID and the PID of the process group. Or in this case, the PID of the process. Each job that has been placed in the background is assigned a unique job number by the shell. This job number. I wonder if job numbers are global. I don't think they are. I think they're local to the terminal. So if I sleep for 60 and throw that in the background, then I do the same thing here. Sleep 60 in the background. Yeah, they're certainly local. Each job that is placed in the background is assigned a unique number by the shell. The job number is shown in square brackets after the job is started in the background, and also when the job is manipulated or monitored by various job control commands. The number following the job number is the process ID of the process created to execute the command, or in the case of a pipeline, the process ID of the last process of the pipeline. In the commands described in the following paragraphs, jobs can be referred to using the notation %num, where num is the number assigned to the job by the shell. In many cases, %num argument can be omitted, in which case the current job is used by default. The current job is the last job that was stopped in the foreground using the suspend character described below. Or, yeah, I use it with Vim all the time. Like, I have Vim loaded, I hit Control Z, now it's stopped, and I use that all the time. Or if there's no such job, then the last job, start in the background. There are some variations in details how different shells determine which background jobs consider the current job. In addition, the notation %% or %+ refers to the current job, and notation %- refers to the previous current job. The current and previous current jobs are marked with plus and a minus sign, respectively, in the output produced by the jobs command, which we describe next. The jobs shell built-in command lists all background jobs. So if I hit Control Z, jobs, I'll see Vim running there with the plus. At this point, the shell is the foreground process of the terminal, since only a foreground process can read input from the controlling terminal and receive terminal-generated signals. Sometimes it's necessary to move a background job into the foreground. This is done by using the FG shell built-in command. Yep. Okay, so you can specify the job you want to foreground. We're using the %sign as demonstrated in the example. The shell redisplays a job command line whenever the job has moved between the background and foreground. Below, we'll see that the shell also does this whenever jobs state changes in the background. When a job is running in the foreground, we can suspend it using the terminal suspend character. Normally Control Z, which sends sig stop signal to the terminal's foreground process group. After you type Control Z, the shell displays the command that has been stopped in the background. If desired, we can use the foreground command to resume the job in the foreground. Use the BJ command to resume it in the background. In both cases, the shell resumes stop job by sending a sig tag. So if I do BG, I've never BG'd at Vim before. BG. It's not resuming. It's like I'm not going to be backgrounded. Doesn't make sense for him to be backgrounded. So it just says, I'm done. We can stop a background job by sending it a sig stop signal. Kill dash stop %1. So you use %1 with kill, yeah. Jobs BG %1. Makes sense. The coordinate C shells provide the command stop as a shorthand for kill dash stop. Stop. When a background job eventually completes, the shell prints a message prior to displaying the next shell prompt, so saying done. Do we really have that much on job control? This is like insane. Jesus Christ, so much on job control. Can't be that complex. It's like a bajillion pages. Alright. Only process in the foreground job may read from the controlling terminal. This restriction prevents multiple jobs from competing for terminal input. If a background job tries to read from the terminal, it is sent a sig t-tin signal. The default action of sig t-tin is to stop the job. So if you cat standard in to text.txt in the background, and then we send some information to standard in, then that thing is stopped. Makes sense? It may not always be necessary to press enter key to see the job state change in the previous example and some of the following examples, depending on the kernel. Scheduling decisions, shell may receive notification about this changes in the state of the background job before the next shell prompt is displayed. At this point, we must bring the job into foreground FG and provide the required input. If desired, we can then continue execution of the job in the background by first suspending it and then resuming it in the background with BG. Of course, in this particular example, cat would immediately be stopped again, since it would once more try to read from the terminal. By default, background jobs are allowed to perform output to the controlling terminal. However, if the toe stop flag, terminal output stop, is set for the terminal, then attempts by the background jobs to perform terminal output result in a generation of a sig TTOU signal. We can set the TO stop flag using the STTY command, which is described in section 62.3. Like sig TTIN, a sig TTOU signal stops the job. So we say, hey, stop date and. Okay. We can see the output of the job by bringing it into foreground. Okay, so that data isn't lost. It stopped before it can write. The various states of a job under job control, as well as the shell commands and terminal characters and the company signals used to move a job between these states, are summarized in figure 34.2. This figure also includes a notional terminated state for the job. This state can be reached by sending various signals to the job, including sig and sig quit, which can be generated from the keyboard. Command, and terminated, stopped in the background, running in the background, running in the foreground. Yep, that's my understanding of things. Implementing job control. In this section, we examine various aspects of implementation of job control and conclude with an example program that makes the operation of job control more transparent. Although optional in the original POSIX 1 standard, later standards including SUSE 3 require that implementation support job control. This support requires the following. The implementation must provide certain job control signals: sig stop, sig t stop, sig continue, sig t tau, sig t tin. In addition, the sig child is also necessary since it allows the shell, the parent of all jobs, to find out when one of its children terminated or stopped. The terminal driver must support generation of the job control signals so that when certain characters are typed, or terminal IO and certain other terminal operations described below are performed from a background job, an appropriate signal is sent to the relative process group. In order to be able to carry out these actions, the terminal driver must also record the session ID, controlling process, and foreground process group ID associated with the terminal. The shell must support job control. Most modern shells do. This support is provided in the form of commands described earlier to move a job between the foreground and background and monitor the state of the job. Certain of these commands send signals to the job In addition, when performing operations that move the job between running in the foreground and any of those states, the shell uses calls to TC set P group to address the terminal driver's record of the foreground process group. In section 20.5, we saw that signals can generally be sent to a process only if the real or effective user ID of the sending process matches the real user ID or save set user ID of the receiving process. However, sig continue is an exception to this rule. Kernel allows a process, e.g. the shell, to send sig cont to any process in the same session, regardless of the process credentials. This relaxation of the rule for sig continue is required so that if a user starts a set user ID program and changes its credentials, in particular its real user ID, it's still possible to resume it with sig continue if it is stopped. The sig-t-tin and sig-t-tau signals. So SOSV3 specifies the Linux implements some special cases that apply with respect to the generation of sig-t-tin and sig-t-tau signals for background jobs. Sig-t-tin, I gotta figure out what these things stand for, or else I'm gonna go insane here. What does sig-t-tin and sig-t-tau stand for? So TTY input and TTY output. Sig TTY in, TTY out. Okay, that's a little bit cryptic, yep. The sig TTY input is not sent if a process is currently blocking or ignoring the signal. Instead, a read from the corresponding terminal fails. Yeah. I don't really care about some of these signal details. I'm skipping over it. Example program demonstrating the operation of job control. The program listed in 34.5 allows us to see how the shell organizes the commands in a pipeline into a job process group. This program allows us to monitor certain of the signals sent to the changes made to the terminal's foreground process group setting under job control. The program is designed so that multiple instances can run in a pipeline, as in the following example. Yeah. The program listing 35.5 performs the following steps. I'm going to read the source code instead of reading the text because the source code usually makes more sense. So let's start at the top here. We got a handler for some signal. We got a main. That's it. So we're using string signal fcntl and the header for the book. We have a static integer that's shared for the global process. And it's called command num. When we receive the signal, we can receive the signal number. We then get our PID, and we say, hey, if your PID is the process group ID, then you're the leader. We say terminal foreground process group, and then we put in the standard error file node tc get process group, and then we also write the standard error process get PID receive signal command num. Process get PID command num receive signal sig, and then the stir signal. So that just tells us that we got the signal, and then if sig is sig stop, then we raise sig stop, which will crash the program, I believe. Oh no, we just get stopped, sorry. When we raise sig stop, we get stopped. Okay. In the main, we set our signal handler up, and I forget what SA restart does. I forget what SA restart does. Can I say man? This will be sig action. SA restart. Oh, that's for Yeah, if you interrupt a syscall with the handler, then it gets restarted. But only in certain cases, not in every case. Because it can't be easy like that. I feel like the design of a simple system has rules that are just always followed or never followed. Like, it seems like with Linux, it's just constant, or with Unix in general, it's like constant exceptions after exceptions. I before E, except after C, except for neighbor and way. It's like, oh god. Anyway, so we register sig in, sig stops to continue, so we can print them out. And then we say if the standard in is a terminal, this is the first process in the pipeline. Print the heading and initial message to be sent down the pipe. So if it is a TTY, then you can say, hey, else it's a pipe, and we're gonna say read into the command now. Why are we reading into command now? Oh, these go to standard error. Okay. Terminal foreground process group. Terminal foreground process group. Interesting. It's the same message. But this is from a signal handler. Okay. Why do we command num plus plus it here? It's being written in here. Oh, command num is then generated then. Command num is 0 here. We add 1 to 1 and then we write it out here. This is the right here. Alright, that makes sense. I'm going to go back and reread the textual description because the code, I understand most of it, but figured it would give me a better understanding if I read this. The program listing in 34.5 performs the following steps. On startup, the program installs the signal handler for sig in, sig stop, and sig continue. The handler carries out the following steps. Displays the foreground process group for the terminal. To avoid multiple identical lines of output, this is done only by the process group leader. Display the ID of the process position in the pipeline, and the signal received. Handler must do some extra work if it catches sig stop, since when caught, the signal doesn't stop the process. So to actually stop the process, we raise it again. The program is the initial process in the pipeline. It prints the headings for the output produced by all the processes. In order to test whether it is the initial or final pipeline, the program uses is_addy function. Check whether the standard input or output is the terminal. If the specified file descriptor refers to a pipe, is_addy returns false. The program builds a message to be passed, so I mean, this is common. Like if you do like ls and then you do ls papped into cat, you see how like it's a different output. If you actually do /ls into cat, it's like way different output, and that's because ls checks to see if standard out file descriptor 1 is a TTY, and if it is, it does different formatting versus if it's anything else. Does the same thing here, but this is for icons and stuff. Okay. Yep. It's pretty much my understanding of the program. So let's continue reading here. The following shell session demonstrates the use of the program listing 34.5. We begin by displaying the process ID of the shell, which is the session leader and leader of the process group of which it is a sole member. And then we create a background job containing two processes, job on and job on, and then we throw it in the background. So the terminal foreground process group is 1204. They have two commands, 1226, 1227, which have the session ID 1224, the process group ID 1226, the PPID, parent PID of 1224, and then of course their own PIDs. From the above output, we can see that the shell remains the foreground process for the terminal. We can also see that the new job is in the same session as the shell, and that all the processes are in the same process group. Looking at the process IDs, we can see that the process in the job were created in the same order as the commands were given in the command line. Most shells do things this way, but some shells implementations create the processes in different order. We continue creating a second background job consisting of 3 processes. Makes sense. We see the shell is still the foreground process group for the terminal. We also see that the processes for the new job are in the same session as the shell, but are in a different process group from the first job. Now we bring the second job into the foreground and send it a SIGINT signal. Control C. So now we got 230, 220, 1230, 1229, 1228 are all receiving the interrupt. From the above output, we see that the SIGINT signal was delivered to all the processes in the foreground process group. We also see that this job is now the foreground process group for the terminal. Next, we send SIG stop signal to the job, or SIG T stop. Type in Control Z to generate SIG T stop. Okay. And then 1228 is still the foreground process. Odd. Thought that might switch back to the shell. Okay. Now all members of the process group are stopped. The output indicates that process group 1228 was the foreground job. However, after the job was stopped, the shell began. Yeah, I was gonna say. Although we can't tell this from the output. When we then proceed by restarting the job using the BG command, which delivers a signal to the processes in the job. So you background it, say, hey, continue, but you're not wired up to the terminal. And then we're going to kill both of them. Is that because we didn't register the... We got stop, continue, interrupt, but we didn't get kill. Kill is... not SIG kill. Term? I think it's SIG term. Just signals. Oh well. Alright, handling job control signals. More. I just hate all this signal handling stuff. Okay, we're getting close. We're getting closer. All right. Because the operation of job control is transparent to most applications, they don't need to take special action for dealing with job control signals. Yeah, because like continue and stop, like these things, the operating system has default disposition that will stop and resume your execution. One exception is programs that perform screen handling, such as VI and less. Such programs control programs that perform Such programs control the precise layout of text on a terminal and change various terminal settings. Don't they use something called like alt mode? There's like the regular terminal output, and then there's terminal alt mode. I think it's called alt mode, something like that. And like that thing is where Vim outputs to, I think. Maybe not. I'm not sure. Let's ask AI. Say with something like curses, does it use alt? Something like alt mode to output control chars and draw the screen. Does NeoVim draw to the alternate screen? Yeah. So there's like some alternate screen mode, and then it just like does all of its like terminal control characters to draw everything. I think that's to like not mess up the history with a bunch of garbage. Such programs control the precise layout of text on a terminal and change various terminal settings, including settings that allow terminal input to be read a character rather than a line at a time. Describe the various terminal settings in Chapter 62. Screen handling programs need to handle the terminal stop signal. The signal handler should reset the terminal into canonical line at a time input mode and place the cursor at the bottom left corner of the terminal. When resumed, the program sets the terminal back into the mode required by the program, checks the terminal window size, which may have been changed by the user in the meantime, and redraws the screen with the desired contents. When we suspend or exit a terminal handling program, such as VI on an Xterm or other terminal emulator, we typically see that the terminal is redrawn with the text that was visible before the program was started. The terminal emulator achieves this effect by caching two character sequences. That program employs the term info and term cap packages are required to output when assuming and releasing control of terminal layout. First of these sequences, called SMCUP, normally escape, causes the terminal emulator to switch into an alternate screen. There we go. Second sequence, called RMCUP, normally escape, followed by so-and-so, causes the terminal emulator to revert to its default screen, thus resulting in the reappearance of the original text that was on display before the screen handling program took control of the terminal. Exactly what I was thinking. When handling sig stop, we should be aware of some subtleties. We have already noted for the first of these in section 34.7.2, if sig stop is caught, then it doesn't perform its default action of stopping the process. We dealt with this issue by having our handler for sig stop raise the sig stop signal. Since sig stop can't be caught, blocked, or ignored, it is guaranteed to immediately stop the process. However, this approach is not quite correct. In section 26.1.3, we saw that parent process could use the wait status value returned by wait or wait PID to determine which signal caused one of its child to stop. If we raise a sig stop signal in the handler for sig stop, it will misleadingly appear to the parent that the child was stopped by sig stop. The proper approach in this situation is to have the sig stop handler raise a further sig stop signal to stop the process as follows. I don't really care about the signal handling. I'm just going to skip over this. It's a bunch of signaling details I don't care about. Orphan process groups. We'll resume there. I just can't read any more signal stuff. In section 26.2, we saw that an orphan process is one that has adopted by a NIT after a parent is terminated. Within a program, we can create an orphan child using the following code. So fork, if it's either parent or an error, then we exit, and then the child is orphaned. Suppose that we include this code in a program executed from the shell. Figure 34.3 shows the state of process before and after the parent exits. So we got A, which is creation of parent and child process. So login shell does a fork and exec for the parent, and the parent does a fork, and the parent then exits, which leaves a login shell. The child is adopted by NIT. And then there's this key thing. Oh no, it's just a indication. Okay. And NIT's in a different process group in a different session. Okay. After parent terminates, child process and figure so and so is not only an orphan process, it's also part of an orphan process group. Subset 3 defines a process group as orphaned if the parent of every member is either itself a member of the group or is not a member of the group's session. Put another way, a process group is not orphaned if at least one of its members has a parent in the same session but in a different process group. If in figure 34.3 the process group containing the child is orphaned because the child is in a process group on its own and its parent, a NIT, is in a different session. By definition, a session leader is in a orphaned process group. This follows because set SID creates a new process group in the new session, and the parent of the session leader is in a different session. To see why orphan process groups are important, we need to view things from the perspective of shell job control. Consider the following scenario based on figure 34.3. More signals. Before the parent process exits, the child was stopped, perhaps because the parent sent it a stop signal. When the parent process exits, the shell removes the parent process group from its list of jobs. The child is adopted by NIT and becomes a background process for the terminal. The process group containing the child is orphaned. At this point, there's no process that monitors the state of the stop child via wait. So it's going to be a zombie. Since the shell did not create the child process, is not aware of the child's existence or that the child is part of the same process group that as a deceased parent. Furthermore, the NIT process checks only for a terminated child and then reaps the resulting zombie process. Consequently, the stopped child might languish forever since no other process knows it's to send it a sig continue signal in order to cause it to resume execution. Even if a stop process is in an orphan process group has a still living parent in a different session, the parent is not guaranteed to be able to send sig continue to the stopped child. a process may send SIG continue to any other process in the same session, but if the child is in a different session, the normal rules for sending signals apply. So the parent might not be able to send a signal to the child if the child is a privileged process that has changed its credentials. Jesus Christ, we're jumping over backwards to get like a weird edge case here. To prevent scenarios such as the one described above, Custody 3 specifies that a process group becomes orphan and has any stopped members, then all members of the group are sent a SIG HUP signal in order to inform them that they have been disconnected from their session, followed by a SIG continue signal to ensure that they resume execution. If the orphan process group doesn't have any stopped members, no signals are sent. A process group may become orphaned either because the last parent in a different process group in the same session terminated, or because the termination of the last process within the group that had the parent in another group. In either case, the treatment of a newly orphaned process group containing stopped children is the same. Sending SIG HUP and SIG continue to a newly orphaned process group that contains stopped members is done in order to eliminate a specific loophole in the job control framework. There is nothing to prevent the members of an already orphaned process group from later becoming stopped if another process with suitable privileges sends them a stop signal. In this case, the process will remain stopped until some process again with suitable privileges sends them a SIG continue signal. When called by a member of an orphaned process group, the TC set P group function fails and calls to TC set adder fail as well. Okay, example program. I'm just going to read the output on this one because I don't care about the where we at here. We go to, how do we get all the way there? 28. Here we go. The following session log shows the results of 2 different runs of the program listening 34/7. Okay. I don't really care about any of this orphan stuff, to be honest. I'm just going to skip it. Summary. Sessions and process groups, also known as jobs, form a 2-level hierarchy of processes. A session is a collection of process groups, and a process group is a collection of processes. A session leader is a process that created the session using set SID. A process group leader is the first member of a process group. All of the members of a process group share the same process group ID, which is the same as the process ID of the process group leader. And all processes with the process group that constitute a session have the same session ID, which is the same as the process ID of the session leader. Each session may have a controlling terminal, dev TTY, which is established when the session leader opens a terminal device. Opening the controlling terminal also causes the session leader to become the controlling process for the terminal. Sessions and process groups were defined to support shell, job control, although occasionally they find other uses in applications. Under job control, the shell is the session leader and controlling processes for the terminal on which it is running. Each job, a simple command or a pipeline, executed by the shell is created as a separate process group, and the shell provides commands to move the job between different states, running in the foreground, running in the background, and stopped in the background. To support job control, the terminal driver maintains a record of the foreground process group job of the controlling terminal. The terminal driver delivers job control signals to the foreground job when certain characters are typed. These signals either terminate or stop the foreground job. The notion of the terminal's foreground job is also used to arbitrate terminal I/O requests. Only processes in the foreground job may read from the controlling terminal. Background jobs are provided by reading. Background jobs are prevented from reading by delivery of the SIG TIM, which is TTYN signal, whose default action is to stop the job. If the terminal's TO stop is set, then background jobs are also prevented from writing to the controlling terminal by delivery of the SIG TTY out signal, whose default action is to stop the job. When a terminal disconnection occurs, the kernel delivers a SIG-HUP signal to the controlling process to inform it of the fact such an event may result in a chain reaction whereby a SIG-HUP signal is delivered to many other processes. First, if the controlling process is a shell, as is typically the case, then before terminating, the shell sends SIG-HUP to all the process groups it has created. Second, if delivery of SIG-HUP results in termination of a controlling process, if the delivery of SIG-HUP results in the termination of a controlling process, then the kernel also sends SIG-HUP to all of the members of the foreground process group of the controlling terminal. In general, applications don't need to be cognizant of job control signals. One exception is when the program performs screen handling operations. Such programs need to correctly handle SIG-stop signal, resetting terminal attributes to same values before the process is suspended, and restoring the correct application-specific terminal attributes when the application is once more resumed following delivery of SIG-cont signal. Process group is considered to be an orphan if none of its member process has a parent in a different process group in the same session. Orphan process groups are significant because there is no process outside the group that can both monitor the state of any stop process within the group and is also allowed to send SIG continue signal to the stop process in order to restart them. This could result in such a stop process languishing forever in the system. To avoid this possibility, when a process group with stopped member processes becomes orphaned, all members of the process group are sent SIG-HUP signal followed by a SIG continue signal to notify them they have been orphaned and ensure that they are restarted. Okay. Okay. I'm not going to do any of those. Chapter 35. Process and priorities and scheduling. Let's go to our, speaking of job control, this is 733 and we are at 244. I'm going to sit down because standing up seems difficult right now. All right. Process priorities and scheduling. This chapter discusses various system calls and process attributes that determine when and which process obtained access to the CPU. Okay, this is more interesting than job control stuff. Okay, we begin by describing the nice value, a process characteristic that influences the amount of CPU time that a process is allocated by the kernel scheduler. We followed this with a description of the POSIX real-time scheduling API. This API allows us to define the policy and priority used for scheduling processes, giving us much tighter control over how processes are allocated to the CPU. We conclude with a discussion of the system calls for setting a process's CPU affinity mask, which determine the set of CPUs on which a process running on a multi-processor system will run. For some reason my Twitch says that I'm offline. Okay, now it says live. Okay. Process priorities, nice values, On Linux, as with most other Unix implementations, the default model for scheduling processes for use of the CPU is round-robin time sharing. Under this model, each process in turn is permitted to use the CPU for a brief period of time, known as a time slice or a quantum. Round-robin time sharing satisfies two important requirements of an interactive multitasking system. Fairness. Each process gets a share of the CPU. Responsiveness. A process doesn't need to wait for long periods of time before it receives use of the CPU. Under the round-robin time-share algorithm, processes can't exercise direct control over when and how and for how long they will be able to use the CPU. By default, each process in turn receives use of the CPU until its time slice runs out or it voluntarily gives up the CPU, for example, by putting itself into a sleep or performing a disk read, or any number of blocking operations. If all processes attempt to use the CPU as much as possible, i.e. no process ever sleeps or blocks on an I/O operation, then they will receive a roughly equal share of the CPU. However, one process attribute, the nice value, allows a process to indirectly influence the kernel scheduling algorithm. Each process has a nice value in the range -20 as a high priority and +19 low priority. So it's like how nice you are. You're like, I don't really need the CPU. I'm very nice. I don't need the CPU at all. Or I'm very not nice. I need as much CPU as I can have. So negative values, it makes sense for them to be higher priority. The default is 0. For it to figure 35.1. Okay, we got a figure here. We got nice value, high priority, -20, traditionally only available to privileged process. Then you got the 0 as the default, and the low priority if you're super nice. The traditional Unix implementations, only privileged processes can assign themselves to or other processes a negative high priority value. We'll explain some Linux differences in section 35.3.2. Unprivileged processes can only lower their priority by assuming a nice value greater than the default 0. By doing this, they are being nice to other processes, and this fact gives the attribute its name. The nice value is inherited by a child created via fork and preserved across exec. Rather than returning an actual nice value, the get priority system call service routine returns a number in the range 1 low priority to 40 high priority, which is kind of like the same thing, calculated according to the formula unice is 20 minus knice. This is done to avoid having a negative return value for a system call service routine. It makes sense, because it's usually to indicate a negative result or a error result, which is used to indicate an error. See the description of system call service routines in section 3.1. Don't care. Applications are unaware of the manipulated value returned by the system call service routine, since the C library get priority wrapper function reverses the calculation, returning the value 20 minus on nice to the calling program. Range and interpretation of process nice value. Effect of the nice value. Processes are not scheduled in a strict hierarchy by nice value. Rather, the nice value acts as a weighting factor that causes the kernel schedule to favor processes with higher priorities. Giving a process a lower priority, i.e. high nice value, won't cause it to be completely starved of the CPU, but causes it to receive relatively less CPU time. The extent to which the nice value influences the scheduling of a process has varied across Linux kernel versions, as well as across Unix systems. Starting in kernel 2.6.23, a new kernel scheduling algorithm means that relative differences in nice values have a much stronger effect than in previous kernels. As a result, processes with low priorities receive less CPU than before. Processes with high priorities obtain a greater portion of the CPU. Boop. Retrieving and modifying priorities. The get priority and set priority system call allow a process to retrieve and change its own nice value or that of another process. Both system calls take the argument which and who, identifying the processes whose priority is to be retrieved or modified. The which argument determines how who is interpreted, this argument takes one of the following values: a process group, or a user. Process operated on the process whose process ID is equal to who. If who is 0, use the caller's process ID. Operate on all of the members of a process group whose process group ID equals who. If who is 0, it's the caller's process group. Operate on all process who real user equals who. If who is 0, the caller's real user ID. Use the caller's real user ID. Okay. Okay. The IDT data type used for the who argument is an integer type of sufficient size to accommodate a process ID or a user ID. The get priority system call returns the nice value of the process specified by which and who. If multiple processes match the criteria specified, which may occur if which is a process group or prio user, then a nice value of the process with the highest priority, i.e. lowest numerical value, is returned. Since get priority may legitimately return a value of -1 on a successful call, we must test for an error by setting error node to 0 prior to the call and then checking for -1 return status and a non-zero error node value after the call. The set priority system call sets the nice value of the process specified by which and who to the value specified in priority. Attempts to set a nice value to a number outside the permitted range, -20 to +19, are silently bounded into this range. Historically, the nice value was changed using a called nice increment, which added anchor to the calling process nice value. This function is still available, but it is superseded by the more general set priority system call. The command line analogs of set priority and are nice, the nice command. Never actually had to use it for anything other than just playing around. So that's running it, running the command with it. Can you give it a PID? Let's ask AI. Is there a way from the shell to give a process a new nice value? Re-nice. Yep, pretty much matches the set priority system call. All right, the get priority system call, I think we already talked about that, right? The set priority system call has the nice value of the processes specified by which and who to the value specified priority. Attempts to set a nice value to a number outside the permitted range. Okay. Oh, re-nice, here we go. Historically, nice values was changed using called nice, which added anchor. Yeah, okay. The command line analogs are nice, which are used by unprivileged users to run a command with a lower priority, or by privileged users to run a command with a raised priority, and re-nice, which can be used by a super user to change the nice values of existing processes. All right. Boop. Okay, we got some nice stuff here, and then overview real-time process scheduling, real-time process scheduling API. The API stuff is just so in-depth. CPU affinity and summary. Okay. privileged capsys nice process can change the priority of any process. An unprivileged process may change its own priority by specifying which as prio process and who as zero, or the priority of another target process if it is effective user ID matches the real or effective user ID of the target process. The Linux permission rules for set priority differ from SUSV3, which specifies that an unprivileged process can change the priority of another process if its real or effective user ID matches the effective user ID of the target process. Unix implementations show some variation on this point. Some follow the SUSV3 rules, but others, notably the BSDs, behave in the same way as Linux. In Linux kernels before 2612, the permission rules for calling to set priority by unprivileged processes are different from the later kernels and also deviate from SUSV3. An unprivileged process can change the priority of another process if its real or effective user ID matches the real ID of the target process. From Linux 2.6 onwards, the permission checks are changed to be consistent with other similar APIs available on Linux, such as scheduling, set scheduler, and schedule set affinity. In Linux kernels before 2612, an unprivileged process may use set priority only to irreversibly lower its own or another process priority. A privileged capsys nice process can use set priority to raise priorities. Since kernel 2612, Linux provided the rlimit nice resource limit, which permits unprivileged process to raise priorities. An unprivileged process can set its own nice value to the maximum specified by the formula 20 minus rlimcur, where rlimcur is the current rlimit nice soft resource limit. An example, if a process rlim nice soft limit is 25, then the nice value can be set to -5. From this formula and the knowledge that the nice value has a range positive 19 to -20, we can deduce that the effective useful range for rlimit nice limit is 1 low to 40 high. Rlimit nice doesn't use the number range 19 to -20 because some negative resource limit values have special meanings. For example, rlimit infinity has the same representation as -1. An unprivileged process can make a set priority call to change the nice value of another target process if the effective user ID of the process calling set priority matches the real or effective user ID of the target process, and the change to the nice value is consistent with the target process rlimit nice limit. The program listing 35.1 uses set priority to change the nice value of the processes specified by its command line arguments, which correspond to the arguments of set priority, and then calls get priority to verify the change. Cool story, bro. Set priority right there, and then we do get priority. Overview of real-time process scheduling. The standard kernel scheduling algorithm usually provides adequate performance and responsiveness for a mixture of interactive and background processes typically run on the system. However, real-time applications have more stringent requirements of a scheduler, including the following. A real-time application must provide a guaranteed maximum response time for external inputs. In many cases, these guaranteed maximum response times must be quite small, e.g. of the order of a fraction of a second. For example, a slow response by a vehicle navigation system could be catastrophic. To satisfy this requirement, the kernel must provide the facility for high priority process to obtain control of the CPU in a timely fashion, preempting any process that may currently be running. A time-critical application may need to take other steps to avoid unacceptable delays. For example, to avoid being delayed by a page fault, an application can lock all of its virtual memory into RAM using mlock or mlock all, described in section so-and-so. A high priority process should be able to maintain exclusive access to the CPU until it completes or voluntarily relinquishes the CPU. The real-time application should be able to control the precise order in which its components processes are scheduled. Okay. Subset 3 specifies a real-time process scheduling API, originally defined in POSIX 1b, that partially addresses these requirements. This API provides two real-time scheduling policies, Schedule RR and Schedule FIFO. Processes operating under either of these policies have priority over process scheduling using the standard round robin. Isn't RR right, round robin? Time sharing policy described in section 35.1, which the real-time scheduling API identifies using the constant schedule other. Each of the real-time policies allows for a range of priority levels. Subset 3 requires that an implementation provide at least 32 discrete priorities for the real-time policies. In each of the scheduling policy, runnable processes with higher priority always have precedence over lower priority processes when seeking access to the CPU. The statement that runnable processes with higher priorities always have precedence over lower priority processes needs to be qualified for multiprocessor Linux systems, including hyper-threaded systems. On a multiprocessor system, each CPU has a separate run queue. This provides better performance than a single system-wide run queue, and processes are prioritized according to per CPU run queue. For example, on a dual processor system with three processes, process A with real-time priority 20 could be queued waiting for CPU 0, which is currently running process B with priority 30, even though CPU 1 is running process C with priority 10. Real-time applications that employ multiple processes or threads can use the CPU Affinity API schedule described in section 35.4 to avoid any problems that might result from the scheduling behavior. For example, on a 4-processor system, all non-critical processes could be isolated onto a single CPU, leaving the other 3 CPUs available for use by the application. Linux provides 99 real-time priority levels, numbered 1 lowest and 99 highest, and this range applies in both real-time scheduling policies. The priorities in each policy are equivalent. This means that given 2 processes with the same priority, one operating under the Schedule RR policy and the other under the Schedule FIFO, either may be the next one eligible for execution, depending on the order in which they were scheduled. In effect, each priority level maintains a queue of runnable processes, and the next process to run is selected from the front of the highest priority non-empty queue. POSIX real-time versus hard real-time. Applications with all of the requirements listed at the start of this section are sometimes referred to as hard real-time applications. However, the POSIX real-time process scheduling API doesn't satisfy all these requirements. In particular, it provides no way for the application to guarantee response times for handling input, and to make such guarantees requires operating system features that are not part of the mainline Linux kernel or most all other standard operating systems. The POSIX API merely provides us with a so-called soft real-time, allowing us to control which processes are scheduled for use of the CPU. Adding support for hard real-time applications is difficult to achieve without imposing an overhead on the system that conflicts with the performance requirements of the time-sharing application that form the majority of the applications on typical desktop and server systems. This is why most Unix kernels, including historically Linux, have not natively supported real-time applications. Nevertheless, starting from around version 2.6.18, various features have been added to the Linux kernel with the eventual aim of allowing Linux to natively provide full support for hard real-time applications without imposing the aforementioned overhead for time-sharing operation. The Schedule RR policy. Under the Schedule RR round robin policy, processes of equal priority are executed in a round robin time sharing fashion. The process receives a fixed length time slice each time it uses the CPU. One schedule process employing the Schedule RR policy maintains control of the CPU until either it reaches the end of its time slice, it voluntarily reaches the CPU, either performing a blocking system call or by calling the schedule yield system call, it terminates or is preempted by a higher priority process. For the first two events above, the process running under the Schedule RR policy loses access to the CPU, is placed at the back of the queue for its priority level. In the final case, when the higher priority process has ceased execution, the preemptive process continues executing, consuming the remainder of its time slice, i.e. the preempted process remains at the head of the queue for its priority level. In both the Schedule RR and Schedule FIFO applications, the currently running process may be preempted for one of the following reasons. A higher priority process that was blocked became unblocked. A priority of another process has raised to a higher level than the currently running process, or a priority of the currently running process was decreased to a lower value than that of some of other runnable processes. The Schedule RR policy is similar to the standard round robin time sharing scheduling algorithm Schedule Other, in that allows a group of processes with the same priority to share access to the CPU. The most notable difference is that Schedule RR policy has strictly distinct priority levels, with higher priority processes always taking precedence over lower processes. By contrast, a low nice value doesn't give a process excessive access to the CPU. It merely gives the process a favorable weighting in scheduling decisions. As noted in section 35.1, a process with a low priority always receives at least some CPU time. The other important difference is that the Schedule RR policy always allows us to precisely control the data precisely control the order in which the processes are scheduled. The Schedule FIFO first in, first out policy is similar to the Schedule RR policy. The major difference is that there is no time slice. On a Schedule FIFO, process gains access to the CPU. It executes until either it voluntarily relinquishes the CPU in the same manner as described for the Schedule RR policy above. It terminates or it is preempted by a higher priority process. In the first case, the process is left in the back of the queue for its priority level. In this last case, when the higher priority process has ceased execution, by blocking or terminating, the preemptive process continues execution, i.e. the preemptive process remains at the head of the queue for its priority level. The Schedule batch and Schedule idle policies. The Schedule batch and Schedule idle policies. The Linux 2.6 kernel series added two non-standard scheduling policies, Schedule batch and Schedule idle. Although these policies are sent via the POSIX real-time scheduling API, they are not actually real-time policies. The Schedule batch policy added in kernel 2.6.16 is similar to the default Schedule other policy. This policy is intended for batch-style execution of processes. The scheduler takes account of the nice value, but assumes that this is the CPU-intensive job that does not require low-latency scheduling in order to wake up events, and thus mildly disfavors it in scheduling decisions. The schedule idle policy added in kernel 2.6.23 is also similar to schedule other, but schedules the process with a very low priority, lower than a nice value of 19. The process of nice value has no meaning for this policy. It is intended for running low priority jobs that will receive a significant portion of CPU only if no other job on the system requires a CPU. I wonder if Docker has or Kubernetes has a nice Sask AI. All right. Real-time process scheduling API. I'm going to take a quick bio break and then I'll come back and pick up where I left off there. All right. I don't know why, but I'm just like completely exhausted this afternoon. And I don't really have the excitement for this material that I thought it would have. It's always good to like check in on our progress. We got that much left. So we're over the hump. We're at page 740. And all the interesting stuff is in the back of the book. So I'm eager to get there. Chapter 63 is like the best chapter of the book. Everything cool is being referenced to chapter 63, which is alternative IO models. I think once I start getting into let's see. This will be a fun chapter. I don't care about that really. This will be a fun chapter, as well as this. I think once I start getting into things like IPC, pipes and FIFOs, System V, IPC, System V message queues, System V semaphores, System V shared memory. I think I should write some like test programs, memory mapping, virtual memory operations, introduction to POSIX IPC, POSIX message queues, POSIX semaphores, POSIX shared memory, like file locking, sockets definitely, sockets Unix domain. Like I want to write more test programs in these chapters that are interesting. So I might need to like slow my roll a little bit on those chapters. Or I could do like I was doing is like put in the exercise ideas into my to-do list, and then when I'm done with the reading, go back and do them. Terminals, I don't care about writing anything. Alternative IMO models, I definitely care about. Yeah, okay. But we're all the way back here to 35. 35, where are you? Here we go. All right. Real-time process scheduling API. We now look at various system calls constituting the real-time process scheduling API. These system calls allow us to control process scheduling policies and priorities. Although real-time scheduling has been part of Linux since version 2.0 of the kernel, several problems persisted for a long time in the implementation. A number of features of the implementation remain broken in the 2.2 kernel, and even in early 2.4 kernels. Most of these problems were rectified by about kernel 2420. Real-time priority ranges. The sketch get priority min and sketch get priority max system calls return the available priority ranges for a scheduling policy. So you give the policy, it gives you the min and max. For both system calls, policy specifies the scheduling policy about which we wish to obtain information. For this argument, we specify either sketch RR or sketch FIFO. The sketch get priority min system call returns the minimum priority. What was FIFO? Did I just like space out on this? I was like zoning it out. Huh. The schedule get priority min system call returns the minimum. The other one's for the maximum. On Linux, these system calls return numbers 1 to 99, 1 and 99 respectively for both schedule and schedule FIFO policies. In other words, the priority range for these two real-time processes completely coincide, and schedule and schedule FIFO processes with the same priority are equal eligible for scheduling. Which one is scheduled first depends on their order in the queue for that priority level. The range of real-time priorities differs from one Unix implementation to another. Therefore, instead of hard-coding priority values into an application, we should specify priorities relative to the return value from one of these functions. Thus, the lowest schedule priority would be specified as schedule get priority min. The next higher priority as schedule get priority min schedule plus 1 and so on. Costudying 3 doesn't require that the schedule R and schedule FIFO policies use the same priority ranges, but they do so on most Unix implementations. For example, Solaris 8, the priority range for both policies is 0 to 59, and on FreeBSD 6.1, it's 0 to 31. Modifying and retrieving policies and priorities. In this section, we look at system calls that modify and retrieve scheduling policies and priorities. Modify scheduling policies and priorities. The set scheduler system call changes both the scheduling policy and the priority of the process whose process ID is specified in PID. If PID is specified as 0, the attribute of the calling process are changed. So you got this set scheduler, you give it the PID, you give it the policy, you give it a struct for the parameters, and PID can be 0 if you want to do it to yourself. The param argument is a pointer to a structure of the following form, which is a schedule priority. SUSV3 defines the param argument as a structure to allow an implementation to include additional information, implementation-specific fields, which may be useful if the implementation provides additional scheduling policies. However, like most Unix implementation links, provides just the schedule priority field, which specifies the scheduling priority for schedule R and schedule FIFO policies. This must be a value in the range indicated by the min and max. For other policies, the priority must be 0. The policy argument determines the scheduling policy for the process. It is specified as one of the policies shown in table 35.1. Whew. Okay. Okay. A successful set scheduler call moves the process specified by PID to the back of the queue for its priority level. SUSV3 specifies that the return value of a successful set scheduler call should be the previous scheduling policy. However, Linux deviates from the standard in that a successful call returns 0. A portable application should test for success by checking that the return status is not -1. The scheduling policy and priority are inherited by a child created via fork and are then preserved across an exec. The schedule set param system call provides a subset of the functionality of scheduler. It modifies the scheduling priority of a process while leaving the policy unchanged. So that just sets the param. The PID and param arguments are the same as for set scheduler. A successful set param call moves the process specified by PID to the back of the queue for its priority level. The program in listing 35.2, which is right coming up, uses set scheduler to set its policy and priority of the process specified by its command line arguments. The first argument is a letter specifying a schedule policy. The second is an integer priority, and the remaining arguments are the process IDs of the processes whose scheduling attributes are to be changed. Okay, so let's go over the program. So it's just a main, has some macro if-def checks. We have sketch.h included in the header for the book. We're receiving argc and argv. Argv is being used here, argc is being used here. We declare a int j, which is used for this loop down here. We have a poll, which is some type of policy, I think, which we get from argv. And then we have our parameter sp, which is ultimately what gets sent in here, but we also write into it here. So we declare all that up front on the stack. Then we say if argc is less than 3, well, if argc is less than 3, that means it's 2 or 1 or 0. Argc is always going to be 1. So we're looking for cases where we don't have 2 arguments provided. Then we do, what is this stir? Man stir chur. Locate character in string. Okay. So it's saying take argv1, which is the first argument. Because argv0 is the command. So the first argument, get the first character, and we see if it's in here. If it's not, then there's a error. You gotta say, hey, it needs to be R, F, or O, because we don't allow these other things. So R, F, and O, batch and idle, are not allowed. Oh no, they allow them down here. It's hard to read this, so I don't like macros. So it says, wait a minute, shouldn't those be in the comparison then? R, F, and O here, right? Policy is R, F, batch, idle, or O. Shouldn't they have B and I in here? Okay, that's a bug in the original printing because it's updated in my book here. And then we go into the policy, argv, we say, hey, if it was equal to real time, then it's schedule real time. If it was equal to F, it's FIFO, batch, I, finally other. And then we say get int on arg2, so this is going to be the value. So the first one is one of 5 characters that determines the type, the policy type. I think that's what they called it, or just called the policy. And then the value is determined by the second argument. We just do a get int on that. And I don't know why, I think this is a helper function, yeah. So then we go in a loop, say for j is equal to 3, j is less than argc, j plus plus. So these are for the remaining things. Then we set scheduler, get long, RVJ. These are the PIDs that we're assigning it to, basically, yeah. Yep. All that looks okay. Privileges and resource limits affecting changes to scheduling parameters. In kernels before 2.6.12, a process generally must be privileged, capsys nice, to make changes to scheduling policies and priorities. The one exception to this requirement is that an unprivileged process can change the scheduling policy of a process to schedule other if the effective user ID of the caller matches either the real or effective user ID of the target. Since kernel 2.6.12, the rules about setting real-time scheduling policies and priorities have changed with the introduction of a new non-standard resource limit, R-limit RTP-RIO. As with older kernels, privileged capsys nice processes can make arbitrary changes to the scheduling policy and priority of any process. However, an unprivileged process can also change scheduling policies and priorities according to the following rules. If the process has a non-zero R limit, oh god, bunch of rules. I don't care about these rules. Retrieving scheduling policies and priorities. We got get scheduler on a PID and get param that writes into the param thing. Makes sense. I'm not going to waste time even going over that. It's an obvious API. Preventing real-time processes from blocking up the system. That seems interesting. Since schedule.rr and schedule FIFO processes preempt any lower priority processes, e.g. the shell under which the program is run, then developing applications that use these policies, we need to be aware of the possibility that a runaway real-time process could lock up the system by hogging the CPU. Programmatically, there are a few ways to avoid this possibility. Establish a suitably low soft CPU time resource, R-limit CPU described in section 36.3 using set R-limit. If the process consumes too much CPU time, it will be sent a SIG-X CPU signal, which kills the process by default. Set an alarm timer using alarm. If the process continues running for a wall clock time that exceeds the number of seconds specified in the alarm call, then it will be killed by a SIG alarm signal. Creating a watchdog process that runs with a higher real-time priority. This process can loop repeatedly, sleeping for a specific interval, and then waking up and monitoring the status of other processes. Such monitoring could include measuring the value of the CPU clock time for each process. See the discussion of the clock get CPU clock ID function in section 23.5.3, and checking its scheduling policy and priority using schedule get scheduler and schedule get param. If a process is deemed to be misbehaving, the watchdog thread could lower the process's priority or stop or terminate it by setting the appropriate signal. Since kernel 2.6.2.5, Linux provides the non-standard resource limit R-limit RT time for controlling the amount of CPU time that can be consumed in a single burst by a process running under a real-time scheduling policy specified in microseconds. R-limit RT time limits the amount of CPU time that a process may consume without performing a system call that blocks. When the process does perform such a call, the count of consumed CPU time is reset to 0. The count of consumed CPU time is not reset if the process is preempted by a higher priority process, is scheduled off the CPU because its time slice expired, or for a schedule.rr process, or calls schedule yield. If the process reaches its limit of CPU time, then as with R-limit CPU, will be sent the SIG-X CPU signal, which kills the process by default. The changes in kernel 2.6.2.5 can also help prevent runaway real-time process from locking up the system. For example, see kernel source file documentation schedule schedule rt group.txt. Blah 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 blah. Preventing child process from inheriting privileged scheduling policies. God, this stuff is so boring. Preventing child processes from inheriting privileged scheduling policy. I don't need to know that. Relinquishing the CPU. Great. There's a schedule yield thing where you can yield back to the kernel and it'll put you in the back of the queue. Schedule R time slice. So schedule R get interval. You can give it a time spec. So change the size of the time slice. That's great. CPU affinity. Yeah, we're cruising now. I mean, some of that stuff, the API stuff, is just like, it's an obvious API. Like, you don't need to like go on and on and on and on and on and on and all the detail. I mean, you do if you're a freaking standard like body person, like you're reading standards and writing standards. Like, yeah, you need to specify all those details, but for a casual reader, it is too much. When a process is rescheduled to run on a multiprocessor system, it doesn't necessarily run on the same CPU. Yeah, that's true. On which it last executed. The usual reason it may run on another CPU is that the original CPU is already busy. When a process changes CPU, there's a performance impact. In order for a line of the process's data to be loaded into the cache of the new CPU, it must first be invalidated, i.e. either discarded if it is unmodified or flushed to main memory if it was modified, if present in the cache of the old CPU. To prevent cache inconsistencies, multiprocessor architectures allow data to be kept in only one CPU cache at a time. This invalidation costs execution time. Because of this performance impact, the Linux 2.6 kernel tries to ensure soft CPU affinity for a process wherever possible. The process is rescheduled to run on the same CPU. A cache line is the cache analog of a page in a virtual memory management system. It is the size of a unit used for transfer between the CPU cache and the main memory. Typical line sizes range from 32 to 128 bytes. Further information, see so-and-so. One of the fields in the Linux-specific procpid stat file displays the number of the CPU on which the process is currently executing or last executed. Sometimes it is desirable to set hard CPU affinity for a process so that it is explicitly restricted to always run on one or a subset of the available CPUs. Among the reasons we may want to do this are the following. We can avoid the performance impacts caused by invalidation of cache data. If multiple threads or processes are accessing the same data, then we may obtain performance benefit by confining them all to the same CPU so that they don't contend for the data and thus cause cache misses. For a time-critical application, it may be desirable to confine most processes on the system in order to other CPUs while reserving one or more CPUs for the time-critical application. The ISO CPU's kernel boot option can be used to isolate one or more CPUs from the normal kernel scheduling algorithms. The only way to move a process on or off a CPU that has been isolated is via the CPU affinity system call described in this section. The ISO CPU's boot option is preferred method of implementing the last of the scenarios listed above. For details, see the kernel source file. Kernel parameters. Linux also provides a CPU set kernel option, which can be used on systems containing a large number of CPUs to achieve more sophisticated control over how CPUs and memory are allocated to processes. For details, see the kernel source CPU sets. Linux 2.6 provides a pair of non-standard CPU system calls to modify and retrieve the hard CPU affinity of a process. Sketch set affinity, sketch get affinity. Many other Unix implementations provide interfaces for controlling CPU affinity. For example, HPUX, Solaris provide p set bind system call. Okay, affinity is a thing. The sketch get set affinity system call sets the CPU affinity of the process specified by PID. If PID is 0, the CPU affinity of the calling process is changed. So there's a CPU set type that I'm not familiar with. Alright, I gotta get off in 15 minutes here, which is nice because I think we'll finish this chapter in 15 minutes at least. So you can set the affinity of a PID or ourselves, and then the CPU set is passed in. I don't know what this type is. We'll have to look at that below, I think. And then I'm guessing the CPU set has a length, so you can pass in an array. The CPU affinity to be assigned to the process is specified in the CPU set T structure pointed to by set. The CPU affinity is actually a per thread attribute that can be adjusted independently for each of the threads in a thread group. If we want to change the CPU affinity of a specific thread in a multi-threaded process, we can specify PID as the value returned by a call to get PID in that thread. Specifying PID as 0 means the calling thread. Sorry, get TID, not get PID, get TID. That makes sense. Although the CPU set T data type is implemented as a bit mask, we should treat it as an opaque structure. All manipulations of the structure should be done. Oh, someone's at my front door. I'll be right back. Alrighty. Let's get this done. We got about 10 minutes before I have to hop off here. Okay, where did we leave off? We were talking about the structure CPU set T, I think. Although the CPU set T data type is implemented as a bit mask, we should treat it as a opaque structure. Okay. All manipulation of the structure should be done using the macros CPU 0, CPU set, CPU clear, CPU is set. CPU 0, give it the set, and it zeroes it out, I imagine. Set allows you to set a CPU into the set, or add a CPU into the set. Setting into a set is like overloading the word set. You should say add into a set, and then you can remove it from the set, and then you can say is member or is element of the set. Reusing set here is like bad API design in my opinion. These macros operate on the CPU as follows. The CPUs in the CPU set are numbered starting at 0. The schedule header file defines the constant CPU set size to be 1 greater than the maximum CPU number that can be represented in a CPU set T variable. 1024, the length argument given to schedule set infinity should specify the number of bytes in the set argument. So you just say size of CPU set T. Okay. The following code confines the process identified by PID to running on any CPU other than the first CPU of a 4-processor system. If the CPUs specified in set don't correspond to any CPUs on the system, then schedule affinity fails with the error E invalid. If set doesn't include the CPU on which the calling process is currently running, then the process is migrated to one of the CPUs in the set. An unprivileged process may set the CPU affinity of another process only if its effective user ID matches the real or effective user ID of the target process. A privileged capsys nice process may set the CPU affinity of a process. The schedule get affinity system call retrieves the CPU affinity mask of the process specified by PID. If PID is 0, the CPU affinity mask of the calling process is returned. So you say, hey, get affinity, gives you back the set. The CPU affinity mask is returned in the CPU set structure pointed to by set. The length argument should be set to indicate the number of bytes in the structure, i.e. size of that. We can use the CPU is set macro to determine which CPUs are in the return set. If the CPU affinity mask of the target process has not otherwise been modified, get affinity returns a set containing all the CPUs on the system. No permission checking is performed by schedule get affinity. An unprivileged process can retrieve the CPU affinity mask of a process of any process on the system. Okay, that's unusual. A child process created by fork inherits its parent CPU affinity mask. And this mask is preserved across an exec. The schedule set affinity and schedule get affinity system calls are Linux specific. The T-schedule set affinity get affinity programs in the project proc pri subdirectory in the source code distribution for this book demonstrate the use of set affinity and get affinity. Summary. The default kernel scheduling algorithm employs a round-robin time-sharing policy. By default, all processes have an equal access to the CPU under this policy. But we can set a process nice value to a number in a range -20 high priority to +19 low priority to cause a schedule to favor or disfavor that process. However, even if we give a process the lowest priority, it's not completely starved of CPU. Linux also implements the POSIX real-time scheduling extensions. These allow an application to precisely control the allocation of CPU to processes. Processes operate under the two real-time scheduling policies, schedule-RR round-robin and schedule-FIFO, first in, first out. Always have priority over processes operating under the non-real-time policies. Real-time policies have priorities in the range of 1 to 99. As long as it is runnable, a higher priority process completely excludes lower priority processes from the CPU. A process operating under the schedule FIFO policy maintains exclusive access to the CPU until either it terminates, it voluntarily relinquishes the CPU, or it is preempted because a higher priority process became runnable. Sorry, my mind was wandering there. A process running under the schedule FIFO policy maintains exclusive access to the CPU until either it terminates, it voluntarily relinquishes the CPU, or is preempted because a higher priority process became runnable. Similar rules apply to the schedule RR policy, with the addition that if multiple processes are running at the same priority, then the CPU is shared among these processes in a round-robin fashion. Okay, that makes sense. A process CPU affinity mask can be used to restrict the process to running on a subset of CPUs available on multi-processor systems. This can improve the performance of certain types of applications. Further information, blah, 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 blah. Okie dokie. All right, I got 5 minutes here to kill before my meeting, but I'm going to hop off here. And then when I get back on, we'll resume at chapter 36. I'll record my progress here. Oops. Foreground? Foreground? Okay. Vim progress. So we're at what, page 753? 753. And we're at 355. So our goal is 782 minus 753, which equals 29 pages left. So that's like 2 hours. So I'll be back on around 4:30. We'll do 5:30, 6:30, and then I'll eat dinner at 6:30, and I should be done for the day. But the main takeaways from that previous chapter here about process priorities and scheduling is the default scheduling is a round robin fair scheduler where regardless of your nice value, you're not starved of resources. Then real-time scheduling is like, okay, we can starve people of their resources if they're not real-time processes. So they're like a set of processes that have such high priority that they can starve out other things in the system. And there's two modes. There's a round robin and a FIFO. The FIFO basically, like for your priority level, you will run until you reach a point where you relinquish control of the CPU. So it's more cooperative in that way. And then the round robin policy, the real-time policy, for a given priority level will actually preempt the process or thread and give each thread in that priority level a fair amount of CPU, or a time slice of CPU, I should say. And there's various ways of changing the time slice sizes. What else? Oh, the CPU affinity. Kubernetes like has the concept of a pod affinity or node affinity, and pod anti-affinity. So affinity is just like where you want to go, and so with CPU affinity, it's about which CPUs you want the process to be running on. So you can basically set up a CPU affinity that's the default for the entire system that gets inherited by all children of the system, that makes to where one CPU, for say like the last CPU, last core of the machine has nothing running on it. And then you could have your workload that needs to have explicit access to a single CPU be the only thing running on that CPU. So it can be more real time. So yeah, or you can just carve up sets of CPUs or whatever. It's a pretty flexible API there. So overall, I learned a lot from that chapter, but again, I think there's a lot of detail that I skipped over because it's just not really like necessary for me to learn all that right now. Besides, I'll forget it. Okay, so I'm gonna break here, and we'll come back in about 15 to 30 minutes to chat about process resources and daemons.